Okay, hello everyone. So today I'm going to cover unit root section of chapter 3. This is basically part 2 of chapter 3. So I'm going to walk you through my notes here. So in the first part of lecture 3, we covered stationarity, right? We looked at different types of stationarity, like the first order weakly, like the second order weak stationarity, etc. Now, in the second part, we are going to go through the process of unit roots. I'm going to do this through my handout because I want to sort of go through the math a little bit more slowly than just slides. And then in part 3, we will cover autocorrelation, which will still sort of use some of the notions we learned in part 1 and 2. Okay. Now, let's first start by defining unit root. If a time series is unit root, that means this time series is non-stationary. Remember the definitions of stationarity? If a series is non-stationary, that means it's changing with time. Either its mean is changing or its variance is changing through time, right? Now, the stationarity concept is less of a problem for moving average type series. I'm going to talk about them in a second, but let's first start thinking about this concept in an AR1 type process. So just to refresh our memories, an AR1 process is basically when we write our series as a function of its past values and an error term. Okay, so when it's in this AR1 process, or when it's in this AR1 form, we basically call this also a random walk model, which means that each period, this variable takes a random step away from its previous value. So an AR1 or a random walk is our starting process. The first thing I'm going to do is keep writing this process in its lag form. So for instance, if AT is a function of AT minus 1 and the error term at that time period, then AT minus 1 is a function of AT minus 2, basically one lag version, and the error term last period, right? So we can keep doing this till the beginning of this process, basically. Now, if you keep plugging this AT minus 1 term up above, you get this functional form, which is AT minus, sorry, I actually want to rewrite that a second, which is AT is equal to sigma to the power 2 times AT minus 1, right? Because once you plug this in, you get that. And then you get phi, I called it sigma, but it's actually phi, phi times epsilon t minus 1 plus epsilon t. Okay. Basically, I just plug in the second equation to the first one. Okay. And then if you keep iterating this, you get this functional form, which is saying we can write our process AT as a function of the first value it gets, that's A0, and all the sum of the error terms together with this phi to the power k as the term that are multiplying them, okay? Now this process, if you notice, is actually an MA infinite form, meaning we were able to write our AT as a function of all the previous error term or the residuals of this process, okay? So what did we just do here? We were able to write an AR1 model as an MA infinity model, okay? Because we choose basically our starting point as an AR1, and through repeated iteration, we were able to get rid of all the autoregressive sections and just write the AT like a process that's just the basically sum of this past error terms, okay? Obviously, there's phi k element there as well, but it's basically a function of past error terms, okay? Now, that's a nice feature for us because MA1, or basically or any MA model, basically, let's see, here I'm looking at the most generic version. Let's see, for MA1, YT is a function of today's error term and the past error term, right? In this case, if you look at the expected value of yt, that will be just equal to 0. Why? Because expected value of the error term is 0. Remember our assumptions from the previous classes. And then the variance of error term is equal to sigma squared. That's also constant over time. So as soon as you reach to a moving average or MA type series, you see that they are almost always stationary, okay? But the AR processes are not that straightforwardly stationary oftentimes, okay? So that's why when we think about the unit root, we're going to think about AR process and have that as our benchmark, okay? We're going to do our analysis based on an AR or autoregressive models. Now, let's continue. So you can think of this section as almost like a footnote, like a, yeah, little footnote showing how a moving average process is always stationary. But now that we've confirmed, so we switch from our AR model, AR1 model to an MA infinity model, we should continue working with this final form to understand what unit root really means, okay? Now, I copy paste that same line to the beginning of this process. Remember, this is just our MA infinite or moving average model. And it basically came out of our AR1 model as we plugged in the previous observations, okay? Now, what I would like you guys to do is think of the stationarity of this process, okay? So we switched from AR1 to MA infinite, but we are not done in terms of the stationarity of this series. Let's look at two main indicators, okay? So the first indicator we were concerned with was taking the expected value of this series, okay? So if you take the expected value of this series at the top, right, as first line of equation, what do we get? The first part is the expected value of phi t times A0, right? That's A0 is just a constant, so it will come off as is, and phi is also just a constant, so that will also come off as is from an expected expectation operator. And then the last term, this part, the part with the residuals, the expected value of that will just be equal to 0, because remember, that was one of our assumptions, okay? So basically, expected value of an AT process that looks like an MA infinity would be phi to the power t times A0. Now let's look at the variance of AT, again, from that same equation. That will be variance of that first term, that is phi t times A0, and then the variance of the second term, and then they're actually covariance, right? So technically speaking, there should be also like the covariance here. I'm just going to call it X and Y. That's the first term and the second term, okay? But when you look at the first term, what do we see? So it's variance of phi to the power t times A0. Once again, phi is constant and A0 is constant. So this object's variance is 0, okay? In the second term, though, something more interesting is happening. So variance of epsilon was sigma squared. And all of that is multiplied by this phi k's. And as part of the rule of taking variance, you need to square these coefficients that are multiplying this random process. That's epsilon in this case, okay? But because this first process had a variance equal to 0, the covariance also becomes automatically 0, okay? So we don't have to worry about this last term. Now, variance of AT then just becomes the variance of the second term, which is just sigma squared times phi to the power 0, if I write it for all the k, phi to the power 2, phi to the power 4, etc. Okay? Now, we need to understand whether these expected value and the variance are stationary, okay? But clearly these two variables now rely on this phi object. So we need to understand these moments based on different phi values, okay? And I also wrote here another footnote on the variance process. I have to take variance of a process, okay? Now let's think of the first case. Okay, so the first case I want you guys to look at is what happens to this expected value and the variance when phi is a number less than 1, is a fraction, okay? So again, remember, this was the AR1 process that I'm just specifying what the phi is, but we should think about the MA process because that's where we draw all the expected value and the variance, okay? So expected value of AT was phi t times A0, right? So if this phi object is less than 1, and if it's raised to some infinite power, that means this expected value will be equal to 0. Okay, so in the most extended sample we are looking at, expected value of this series, if phi is less than 1 in absolute value, will be equal to 0. That's great for us because we don't really care if it's 0, but we were looking for the criteria that this expectation should be constant, right, for stationarity. So we kind of get that from here. That's good. Now let's look at the variance. The variance says, remember, this was the same equation I just copied here. We need to calculate this right-hand side, this part, right, this star. And we need to find the whole summation when phi is less than 1. Well, luckily, there is an algebra rule that is like, if you have the sum till the infinity of an object, you can actually rewrite it as 1 over 1 minus x, right? This is something you can only apply if x is less than 1 in absolute value. So what is our x in this case? It's phi squared, right? So if you take the star into phi square parentheses, you get the same thing. 1 plus, 0. Okay. No, actually, I shouldn't do that. We don't even need to do that because it's already in that form, right? It's already phi to the power is 1, actually. So I don't need to take an additional parenthesis. Good. So this is just saying your x is phi squared. Just proceed with that. Okay. So what is our constant then looking like? Sigma squared divided by 1 minus phi squared. Is this constant? Yes, that's great. Okay. So then we can conclude that our AR process would be stationary if this phi object is less than 1 in absolute value. Okay. Basically, we found that the mean and variance are constant. Now let's look at another case where now phi is greater than 1. Well, clearly we can see that now the expected value would become infinity because phi is just a number greater than 1, so it will explode if it's raised to some infinite power. Similarly, for the variance, you will see that if phi is greater than 1, the more exponents you take and then you sum it up, it will also be non-stationary. It will converge to infinity. Okay. So the case where phi is greater than 1 in absolute value would yield us a non-stationary series. Okay. Now the final one is when phi is equal to 1. Okay. This could be that phi is equal to 1 or phi is equal to minus 1. Okay. Let's think of the case where phi is equal to 1. So when phi is 1, this object becomes 1 to the power t, which is just 1. So expected value of AT will become A0. That means the starting value of our series becomes the mean over time. Again, for us, it doesn't matter. What we are only looking for is whether that is constant. Okay. And then when you look at the variance, again, for when phi is just equal to 1, it will be 1 plus 1 plus 1, that is t times. So the variance becomes sigma squared times t. Again, this is non-stationary. It's time dependent, right? So if you look at this series, and if you plot an AR1 series, and I will actually do this in Excel, it will actually look something like this, okay? Which when you see in the graphical form, you would know that it's non-stationary, right? But now I'm sort of giving you guys the parameters that are actually bringing those non-stationarity, okay? The critical with the unit roots is that sometimes it's not super easy to get it visually, the non-stationarity visually, basically. So that's why it's important to have the equation and work from there. But oftentimes you can also, read this from an equation if you are given an equation. So basically what we saw is that if the phi is equal to 1, which means our series has unit roots, we just show that it will be non-stationary because the variance is a function of time and it's not constant. Okay? So what do we do if we have a series that has unit roots? Well, the first thing we can do is take first difference. Okay, so suppose we have this series AT, right, where phi is 1, right? That's the unit root case. Then you take the difference and you say, okay, let's AT minus 1 be my series. So if you do that, from here you can see, you'll basically get epsilon t as your series. Well, this is just an MA series, right? So basically, you take the expectation of dt, that becomes the mean of the error term, that's 0. And the variance of dt, that just becomes variance of epsilon, that's sigma square. These are both constant, so it's stationary. Okay. Okay. Now, we have a test to actually understand whether our series has a unit root in them. Okay, so suppose we have an equation that is yt written as a function of yt minus 1 and an error term. Okay, so now that you saw all different sort of regions of phi, you know that the phi being equal to 1 is the unit root case corresponding to non-stationarity, right? We just showed that the unit root is non-stationary. So what would our alternative hypothesis be then? Because the alternative hypothesis says it should be stationary. And remember, that was only achieved when phi was less than 1. So this is the case of no unit root and the time series being stationary. Okay. Now, the first thing we do here is take first difference. So you can deduct the series yt minus 1 from here. That will be basically giving you this delta yt, that's the left-hand side. And then on the right-hand side, you'll get some mu plus delta times yt minus 1. Okay. Now, in this case, notice we switch from the phi to delta now. And the difference is that phi is now delta is now phi minus 1. Okay. So basically, it's this object. Okay. So now, under null, okay, so under this null object, the left-hand side object, that is the change in yt, is stationary, okay? But then, again, under null, the yt itself is non-stationary, okay? So this brings us a problem. So we can't just use our all t distribution. What we will instead use is a Dickey-Fuller distribution. So there's a whole paper written on it. It has its own critical values. It's the same process. It's just sort of think of it as like a different table because the left-hand side is stationary and the right-hand side is not, okay? You don't need to know the details of this, but all I want you guys to know is that now we can sort of write the null hypothesis in the form of our delta, which is delta being equal to 0 versus delta being less than 0. Once again, they correspond to the series being unit root versus the series being stationary. And the process is very simple. So because this is a one-sided test, right? The left-hand side, as you can see, becomes our rejection region. It's a one-sided test, remember. So if our t statistic is less than the Dickey-Fuller critical value, which I will give you guys if I ask a question on that, we would reject the H0, that is the null. If you reject the null, as you can see from up there, that means our series will be stationary. And in contrast, if you don't reject the null, you will probably be looking at a non-stationary series. Okay. Now, the final thing I want to go through is augmented Dickey-Fuller test. So this is same as Dickey-Fuller test. The only difference is that now we're looking not just an AR1, but ARP process. when this happens, you basically write your YT or change in YT as a function of lag changes in YTs and a YT minus 1. And the null hypothesis is built on this delta term. Okay, so same null as before. Delta being equal to 0 is the case of unit root. If it's less than 0, that's the case of stationarity. You do the same test. The only difference is that you basically write the delta YT as a function of all its lags and the YT minus 1. Again, the only difference here is this is an ARP process. It's not just AR1, so for different lengths. Whereas this one, just the decay fuller, is just on an AR1 process. Okay. All right. I'm now going to show you guys I'm going to show some Excel processes on this just to sort of visually show you guys what different files look like and visually whether they can actually correspond to a stationary or non-stationary series. But this was just a sort of algebra and the hypothesis test building section. And I will continue in class about the sort of more application. Okay, thank you so much.